Welcome back, bugs and germs. We are going to talk about displacement, velocity, and acceleration graphs today. So we're going to look at not so much really quantitative stuff, but more qualitatively, what should the graphs look like? How can we move from one graph to the other? Getting used to looking at some slopes. And then we'll look at one kind of word problem, drawing some graphs. Hopefully it's not too bad. Hopefully it's concrete enough that you guys can get a good handle on it and not just so abstract. Yeah, I don't know. I'm excited. I hope it's a good time for you. I really do like graphing. I think it's super zen. You know what I mean? There's nothing quite like chilling and just drawing graphs. So make sure you maybe got some graph paper handy, or you might want to zoom through the slides real quick. Here, look. See all these graphs you're going to need? You're going to need like 3 per page, something like that. So, all right, let's go talk about them. Let's start by formalizing how everything relates to each other, writing down some explicit information so that we have it somewhere and it's been written down and you've seen it written and it's not just something that I've said out loud to you, so that you know what you should know, right? So we're going to run through all 3 graphs really quick. We're going to talk about what the math property of the graph corresponds to physically, right? Because graphs are math, physics is real life. We've got to somehow put into our brains how the math corresponds to real life, what it means, right? So let's start with our displacement as a function of time graph, sometimes called, come on now, give me a pen. You god dang son of a gun. All right, here we go. Now it's all fixed. Sometimes it's called x verse t. Might see it that way too. But displacement on the y-axis, time on the x-axis. So I'm going to just draw a generic position time graph. Here, we'll make it look like that. Okay. The numbers are not important. We need to talk about just what do the key features of the graph represent physically. So the first and most important thing you need to know about a displacement time graph is that the slope is velocity. So if we look at a tangent line like that, whatever the slope right here where that tangent line touches the graph is, this tangent line is going to tell us the instantaneous velocity of this function, whatever it is. Sometimes I really wish you guys knew calculus. It would make my life so much easier. But it's fine. It's not necessary. It's just easier. But slope is velocity. Most important thing. The next important piece of information that an x versus t graph will tell us is this point right here, our y-intercept. This is our initial displacement. The other thing we can look at on a graph is the area between the graph and the x-axis, or the time axis in this case. For a displacement as a function of time graph, the area under the graph is absolutely meaningless. It doesn't tell you any physical quantity about real life. It's a math thing that you can absolutely calculate and figure out, but it doesn't correspond to any real life thing. In fact, let's look at the units of it. Area of a graph is y units multiplied by x units. So this would be a meter times a second. Not a meter per second. This would be a speed or a velocity. A meter times a second. Like, what can you think of that's measured in meters second? Like, it's physically meaningless. It doesn't, there's nothing like that. And it's not like one of those like abstract things where we're trying to hide it from you and it's going to be a sweet surprise later. Like when your mom tells you, no, honey, we didn't get you a pony for your birthday. That's outlandish and ridiculous, and why would we ever get that? And then on your birthday you wake up and then there's a pony. It's not like that. It's not going to happen, right? It's like when you ask your parents for Xbox Live 3 years in a row for your birthday and they never get it for you. It's like that. All right, let's move on to our velocity as a function of time graph. In this class, we will not really see anything curved for velocity versus time. We will only see linear graphs, and the reason for that is because we're going to look at the velocity formula. V final equals V initial plus acceleration times time. Because this is a linear equation, we're going to limit our learning to linear velocities. And if they can't be represented linearly, we're probably just not going to graph them. Or we'll think of a new way to define it so that they do become linear. Particularly when we start moving in circles later. So let's just look at a graph, maybe a nice simple one like this, right? Dot. We don't want it to go on forever. Real life doesn't go on forever, unfortunately. Sorry if your parents never told you. So for our physical quantities we should know about, the slope of this graph, meaning the slantiness of it, the slope is acceleration. And that makes sense, right? Acceleration is in the y equals b plus mx. Acceleration is the rate of change of velocity. So rate of change on a graph is the slope of a graph. So our slope tells us acceleration. The y-intercept tells us our initial velocity, right? It's the velocity we have when time equals 0. For velocity as a function of time graphs, the area is important. It tells us delta x, or it tells us the change in displacement from the beginning to wherever we measure. Something important that we want to take note of, though, is even though this shaded region here tells us delta x, we can't find an initial displacement. All right, I can't avoid it anymore. I have to tell you about calculus. Okay. And you could feel free to forget this, but in like 15 weeks, when you get to this in calculus, you're like, oh, I learned about that, right? Okay. So there's a fancy math name for area under the graph. It's called an integral. Okay. The integral has that symbol. This is a math symbol. It's an integral. Okay. When you integrate a function over some variable, you're going to get an equation. Let's just say that it's, 3x squared plus 1x. Okay. When you do what's called an indefinite integral, where you don't know the endpoints, you have to take your answer, 3x squared plus x, plus c. In math, you're going to add this plus c. It means plus some unknown constant we cannot determine. You have to tell it to me. This plus c in math corresponds to things like initial displacement or initial velocities. It's an initial condition that you can't figure out from this graph. Someone has to tell it to you. And we'll look at why this happens on the next slide. Okay. All right. So slope is acceleration. Y-intercept is our initial velocity. Area underneath the graph, or rather between the graph and the x-axis, is change in position. And what's important to note is that we can't figure out the initial position from this graph. Someone has to tell it to us. Okay. Last graph that we're going to look at, and these are acceleration graphs. Because for acceleration in this class particularly, we're going to look at either constant accelerations or accelerations that are what are called piecewise graphs, meaning they're going to look like this most of the time. Okay, they're always going to be horizontal lines, and if they're not, we're going to find a different way to describe them, because these graphs, maybe a graph like this, is kind of out of our scope, right? At some point, we could just put, all right, and then here's the jerk first time graph, and here's the snap first time graph, and here's the crackle first time graph, and it becomes weird where you want to stop, right? It's like, well, why did you stop there? So acceleration is really kind of one of the last places that physics really has like a really good definition. From there on out, it becomes really engineering-y, and it's like, well, it's this for this specific material, or it's this for this kind of metal. You know what I mean? It gets too hyper-specific for us to worry about, okay? So don't trip. What I'm trying to tell you is we're going to look at the easy baby stuff, and the harder stuff will be for later, or we're going to find neat tricks to avoid it. So we're going to look at graphs like this. And these are supposed to be horizontal, but I can't draw straight lines. So technically, the slope of this is jerk, but it's not going to matter in this class because our slope is always going to equal 0. And if it doesn't, we're going to hand wave it away. The initial, or the y-intercept, is initial acceleration. So right there, that would be your starting acceleration. But again, we're not really going to be changing acceleration, so it won't matter. Here's where stuff starts to matter, and here's stuff you will be responsible for calculating. The area under an acceleration versus time graph is change in velocity. Okay, let's look at this. Okay, area under A versus T is V. Area under V versus T is X. Do you see what I mean? Whenever you find an area, you go backwards one, what would you call it? One dimension, I guess? One rate of change level, I suppose. In math, you would call it one derivative, right? But you're going back one step whenever you take a area. And then you can go the other direction. Every time you look at the slope, you move this way through the graphs, right? Slope of x versus t is v. Slope of v versus t is a. Slope of a versus t would be jerk, but we're not jerks, so we're not going to worry about it. Okay, so area is change in velocity. Just like on a v versus t graph, we can't determine the initial position. On an a versus t graph, this only tells us what our change in velocity is, not where we start and not where we end. They have to say you start at 5 meters per second. Given the acceleration versus time graph, what's your final velocity? But they still had to tell us v initial equals 5. Okay. If they don't explicitly give you this information or this information, if they don't tell you the start or the end, you can't find either one. Important to keep in mind, delta v equals v final minus v initial. If you know this, you can't find either of these because you have one equation and two unknowns. It kind of breaks this thing called the fundamental theorem of algebra, which says for every equation or every unknown you have, you need at least that many equations to be able to solve it. But I digress a little bit. That's a little more math than maybe we bargained for. Anyway, the idea is you can't find the start or the end, just the change. All right, cool. So now that you're thoroughly disgusted and you're like, ugh, I didn't know physics was just math in disguise, let's go do some math. All right, so we're going to look at a couple of examples where we go through just looking at the shapes of graphs and then trying to figure out the shape of these other graphs. Okay, So we're going to start with a position time graph, and then we'll get v and a. Then on this one, we'll start with a velocity time graph and get a and x. And then on this one, we have a neat scenario that we're going to look at. And then we're going to make all three of them by picking out information from this scenario. Okay, so let's start by looking at this. They don't give us any scenario. They don't tell us a ball is rolling or being thrown or any masses are being pushed. It's just, here's some graphs, make the other ones. So to find velocity, how do I find velocity on a position time graph or a displacement time graph? I'm going to say position every time because that's the way I think about it, but they're interchangeable. Okay, so the velocity on this graph is the slope. So what we're going to do is we're going to look at little tiny tangent lines and try and just guess what the slope is, right? So if I look right here at the y-intercept, or the initial position, this looks pretty flat, right? So the slope here is pretty darn close to 0. Then if I go over a little ways, let's put some markers, right? There we go. If I go over a little ways, now we're facing down a little bit. So I have a small negative slope. So we'll go over a little bit, and we'll go down a little bit, because the slope here is the value here. So it's a small negative valued slope, so we have a small negative value here. I go over a little more. This thing looks a little bit steeper now. So it's a little bit more negative. So we're going to go over again, a little more negative. We go over again. Now that thing's looking really negative. So we're going to go really negative. And here, we're facing pretty far down. That's almost a 45-degree angle, so maybe a little bit more negative. And our velocity is going to look about like that. Again, this is very qualitative, meaning we're not really putting in numbers. We're looking, we're eyeballing it, and then we're making good guesses. Okay? We'll worry about putting numbers in later. All right, so here's our velocity time graph. Notice this thing looks pretty linear the way I've drawn it. So now we need to go from velocity to acceleration. Again, we're going to look at the slope of this line. Slope equals acceleration. So we don't care about the value. I don't care how high up or down this graph is. I just care how slanty it is. The way I've drawn it, this looks like a pretty constant negative slope. It doesn't bend. It's a straight line, and it's pointed down and to the right. So we would say it's negative. Okay. So what that means for us is, let's say it's a -1 slope, right? That means right there is that -1 slope. Right there is at -1 slope. Right there is a -1. Right there is a -1. So for acceleration, we'd be at -1, still -1, still -1, still -1, and we get a horizontal line. Okay, so every time you move over, you should be getting a straighter and straighter and less interesting line. Yeah. All right, cool. All right, let's maybe start in the middle and then we'll go backwards. If you really, really want, I can make up one. I didn't think that it was really necessary to do this one because we're going to learn everything we need here. But if you're still confused, let me know, and then we can do a few more examples. Okay. So now we have a velocity time graph. And there's maybe two ways you can think about this, right? We can either... Actually, let me start that over a little bit. Okay. Let's do the easy part first. Let's find our acceleration time graph. This section here all has the same slope. It's a constant negative slope. Maybe it's -1. We can't see a scale, so it's kind of whatever. But it's constant and it's negative. So that means we're going to have a constant negative value for this first section. Now here, even though velocity is not 0, we're moving in the negative direction at some constant rate. we're at negative 5 meters per second, negative 5 meters per second, negative 5 meters per second. So every second we're moving 5 meters backwards. Okay. The slope here, though, our rise over run, we aren't rising or falling at all. So the slope is 0. That means our acceleration is going to come up here and be on the time axis. You can put a little dotted line to indicate the jump there if it makes you feel better. But notice, you can be moving with an acceleration of 0. Sometimes that feels unintuitive to students. They don't like the idea of moving but not accelerating. It's going to feel even worse when you get told why you accelerate. You're going to be like, why do things do that? Because in real life, this is real life, but in the world that you live in, this scenario is so bizarre. This is not a thing that you will find happening very often because you don't live in a vacuum. So, okay, I've got a really great joke for that later. Stay tuned. Make sure you tune into the next exciting episode of How Physics Works. All right, now let's do the hard part. We have to go back a step. We have to find our displacement versus time graph. And there's maybe 2 ways you can think about doing this. You can either think about, the area between a velocity time graph and the time axis is our change in displacement. I find that way very hard, but it's possible. You can absolutely do it that way, but I find it not nearly as intuitive. Okay. Let me show you how I try and visualize this and think about it, and that's what works for me. If it doesn't work for you, let me know, and then we can do it the area way. Okay. What works for me is looking at the value of our velocity time graph and then making that the slope here. So let me show you what I mean. Right here, we have let's say a medium-sized positive number. So the slope here has to be positive, meaning up to the right, and we want to make it a medium-sized number. So the bigger the number here, the steeper the slope. The smaller the number, the more shallow the slope. So the higher this goes, the more your graph turns that direction. And the lower it goes, or the closer to the time axis, the flatter this graph should get. Once we go below here, it turns negative, and then your graph should start to point down. So what we're going to do is we're going to look at these values and then make little tangents, and then we're going to try and connect them as smoothly as possible. So we need a positive tangent, and it needs to decrease until it gets to about 0 there. So let's go over about there. So it's going to curve over until it gets to being flat, meaning the slope is 0. Then it continues to curve so that it has a negative value until maybe about here. So it's going to roll over like that. And now that this section is constant velocity, that tells us we need a constant slope, so then it becomes straight. So there's really 3 sections here. There's the positive slope section, which is this. There is the decreasing negative slope section, where the graph continues to curve and get more negative sloping, right there. And then there's this section right here, where it's constant, and then because the velocity isn't changing, the slope of this graph isn't changing, and it becomes linear past that point. So we can see the 3 distinct sections of this graph where our velocity is slowly decreasing. We stop. We start moving in the negative direction. So we're going farther away, farther away, farther away. Stop. Start coming back, coming back at a constant rate. Okay. That's how I think about making position time graphs. Notice, though, let's look at our position time graph. Can I move that? Let me lock this in place before I goof up the whole graph. Okay, let's lock these. let me try and show you graphically why you can't find position initial from this graph. On the last slide over here, we said that you cannot determine the initial position from a velocity time graph. Let's try and figure out why. If we look at this graph, let's go ahead and let's first erase these two dots. Okay, let's go ahead and stick all this stuff together. Let's group it so that it's one graph instead of three separate graphs. Let me move this thing. Watch this. Okay, so I've definitely changed our starting position, correct? First, we started right here. Maybe this is like 3 meters. Now I moved it down and we're starting at 0 meters. Okay. Because this is telling me the slope. Did the slope of this graph ever change? No, absolutely not. This is still the same shape. This is still a positive slope, 0 at the top, turning negative, constant negative. But our initial position changed. That's because this initial position, it doesn't have anything to do with the slope, and this is the slope. So if we want to know any information about this thing, you can't tell the slope, right? You have to have some additional information. Think about when you're in your math class and they say the slope of a graph is -3. For you to be able to make the graph that they want, they have to say and goes through 2, 4, right? They have to give you some extra information. Otherwise, a graph with a slope of -3, that could be this, or it could be this, or it could be this, or it could be this. All of these have the same slope. They're all parallel lines. The slope has absolutely nothing to do with the y-intercept. You need this extra piece of information to be able to find it. So that's why we can't tell what the initial position is from a velocity graph, and we can't tell what the initial velocity is from an acceleration graph. It's because these are graphs of slopes, not of y-intercepts. So hopefully that helps you understand why that information is not there. All right. Now that we've really beaten you guys over the head with math today, let's look at a physics problem. All right. So it says a ball is thrown upwards into the air from a person's hand, then falls down to the ground. The ball is in free fall. We'll define this later. Don't worry about it for right now. Basically, it's just saying the ball is flying through the air without any helicopters or parachutes or rockets or anything. It's just doing its own thing, you know. The ball is in free fall and has a constant downward acceleration of 10 meters per second squared. Make a qualitative graph of the situation. Okay, so again, qualitative means we're worried about shapes, not numbers. I know that you have a number here, but we're not going to trip too much about that, all right? Okay, so let's start with the most easiest, that's probably not good English. The easiest graph, it straight up tells us constant downward acceleration number. Constant meaning horizontal graph. Downward, we'll take down to be the negative direction and up to be the positive direction, as all things should be. So we'll say that that's negative. They're saying in the negative direction. And an acceleration of 10. It's really not important what this is. This is just a little bit of foreshadowing. So we're going to just make it a constant horizontal negative number. And if you really want to, you can label that 10 right there. All right. So here is our acceleration graph. Now we need to work our way backwards and get our velocity graphs and our position graphs. Okay. let's take some time to talk about this velocity graph really quick. All this tells us is we need a constant slope of negative 10. Okay. So let's just make a negative 10 slope. There you go. Whatever that slope is, whatever the scale on this is, that's negative 10. Okay. Does it matter if I do that? Is the slope still negative 10? Yeah, absolutely. Is this slope still negative 10? Mm-hmm. What about that one? Yeah, 100%. But depending on where we put this, we're going to get very different position versus time graphs. So let's talk about our three, I guess, really distinct options. Let's talk about this one. Let me copy this. Copy. Pasta. Let's talk about if velocity starts at 0. And then let's talk about if velocity starts at some positive number like that. Okay. And we'll even color code them. Let's do teal is negative. Let's do this nice pink one, starts at 0. And then let's do this blue one, starts here. Okay. We're going to do some math real quick, and then we're going to go back and remember that this is a real problem, and then we're going to talk about which one's correct. Okay. So just for fun, for the sake of math, we're ignoring this problem really quickly. Okay. If our velocity starts negative and gets more negative, that means we start with a negative slope and it's going to just get more negative. So we're going to start with a negative slope and then get more negative like that. Okay. Now let's look at this pink one. It's going to start at 0, so our slope is going to start horizontal and then it'll curve off and get more negative. Like that. And then let's talk about this blue one. Starts positive. Right there, when velocity is 0, it should be horizontal. And then here, it's going to curve off and get more negative. So starts positive, curves off to 0, then gets more negative. Well, what shapes do these look like? Parabolas. Okay. This makes sense because we have x equals 1/2 acceleration times time squared. What happens when you have a squared in math? Y equals 1/2 some number x squared. This thing's a parabola. This thing's a parabola too. So because we're graphing a quadratic function, we should get some parabolas. And these look kind of parabola-y, right? Okay. Now let's go back and remember that we're actually in real life and not all three of these are correct. Okay. A ball is thrown upwards. Okay. If I throw something upwards, it's moving. That's the velocity. Upwards is positive. Okay. So that means at the start, when I'm throwing the ball up, we're saying we're giving it an initial positive velocity. This is telling us where to start at. It's saying velocity is positive at the beginning. That excludes this graph and excludes this graph. So this blue one is the correct velocity graph for this situation of throwing a ball up. Now let's talk about our position time graph. It's thrown up into the air from a person's hand. Okay, so maybe it has a little bit of height, right? If we're looking at the situation, we've got this person gives a little toss, it goes like that, and then it's going to hit the ground, right? And they're happy because they're playing ball in the house. Okay, so it'll have some initial position above the ground because we're starting at a positive displacement, right? X initial is this height. Then it goes up because it's being thrown upwards, right? So it's going to go up, up, up. That's the top of the arc right there. And then it's going to fall down. We should definitely stop right there, though, and get rid of this chunk because it says, then falls down to the ground. let's say that our displacement equals 0 on the ground. A lot of times that's the best choice, right? You want to say the ground is 0. That's a nice reference point. Of course, you could say your hand is 0, x equals 0 here. Then if you go below this mark, these would all be negative, and we would want that negative piece there. But it depends on how you define your system. So start with a constant velocity, or rather acceleration. Read the question thrown upwards. That's the hint that tells us where our velocity graph starts. And then we can move to looking at our position versus time graph. All right. I understand that's a lot of graphing. That's a lot of looking at shapes that you've probably never looked at before. If you have questions, let me know. This is where physics starts to get really overwhelming for people. If you're not overwhelmed right now, don't let me tell you any different. You don't have to be overwhelmed. If you're like, man, that makes total sense, great. That's perfect. I'm glad it's so easy for you. But if you are a little confused or you need some clarification, let me know. Until next time, have a wonderful day, ladies and gentlemen.